Greetings, physicists. This lecture will be about work and energy. And you're going to find that I put a lot more emphasis on the word work than I do on energy because I think for the large part, energy is misunderstood. But work is fairly straightforward. So let's start with work. I have a box sitting on a table, and I am going to try to do work on that box with my hand, and so I push really hard with a big force on that box, right down into the table. And the box doesn't go anywhere. Ladies and gentlemen, I have not done any work from the perspective of physics. There was no work done in this scenario. Well, let me try again. Same box, same table. Now you give it a really big force like this. And the box, here we go, I apply that force, and the box actually winds up over here with me applying this constant force, right? It's my force that pushes the box for a certain delta x. According to a physicist, I have now done work. My force was useful. My force accomplished something. Up here, my force did not accomplish anything. I pushed really hard. I made myself very tired, but I did no work. I did zero work on the box because it didn't go anywhere. So in order for you to do work on something, you can't just exert force on it. You have to move it. You have to make it go somewhere. So we're going to make this definition here, that the concept of work is equal to some force, and we're going to multiply that force by how far that object travels. This is just some definition. Okay? Work is how hard you push, but it's also how much you accomplish, how much distance you go. Pretty simple equation. And if we look at the units for work, well, forces is measured in newtons and distance are measured in meters. So you could say that a unit of work is a newton meter. And remember that a newton, if we go back, was a kilogram meter per second squared, a mass times an acceleration, times this meter. So this is a work unit would technically be a kilogram meter squared per second squared. That's a unit of work. It's a messy unit. And we want to honor some more famous dead physicists. So in honor of Mr. Joule, we will call 1 kilogram meter squared per second squared 1 joule, which is the same as 1 newton meter. Okay? So this is how we're going to measure work in a unit we've called joules. So what makes the work concept interesting is that it's tied up in forces, and forces are universal pretty much. They apply to almost every situation in physics. I would say the core of understanding physics is really about understanding forces. And you can do it in any direction. If I wanted to lift that box, right, instead of sliding it across the table, I could put a force up on the box and I could lift it up to this point. I could do vertical work on it. Let's say it goes up 1 meter. I just did work on that box. This is every time you go to the gym. You're lifting heavy things. You're doing work on them, as long as they move. And so this is the same thing. Work can be, let's see here, we have some special situations with work. For instance, if I had that box sitting on a table, and I attach a string to it, and I try to do work like this by putting tension on the string, and the string is at some angle theta, and the box slides in this direction. This is an interesting situation because I've given the tension is going off at some angle here, so there's really components of that tension, and that tension has a component here, which would be the cosine component, a t cosine theta, that's pulling that box to the right, and then we have a t sine theta component pulling the box straight up. if we watch where the box goes, if the box only moves to the right but doesn't move up, then we have this situation that the force to the right actually caused the displacement, and the force up did not cause a displacement. It didn't cause a vertical displacement. So really, only this force here, the horizontal one, actually did any work on this box. So while I may have put in t worth of force on this box, I only got t cosine theta that contributed to the work. So sometimes you'll see the work equation written like this. Work is equal to F delta x cosine theta, where theta is measured from the direction that from the displacement to the direction of the force. So that's an equation there, that you can only get the maximum out of your force if it is directly in line with the displacement. This also allows for things to be negative. So let's talk about doing negative work. Work is a vector here. I can have a box, again, that I'm going to hold by a string. Like my hand comes out here, right, and holds this string with a box on it. And I'm holding on to it, and I'm going to lower the box to the ground. So if I'm drawing this, the box is up here. And then when I'm done with it, I'll just redraw it to the side here, but you kind of get the idea. There's my hand got bigger. I lowered the box this way, down to the ground. Now let's think about my force. My force, the force of my hand and the tension of the string pulled up. But the box's displacement was down. They are 180 degrees to each other. Well, it's the cosine of 180. That's minus 1. So I have done negative work on that object. If we draw a free body diagram for that object, my force, the tension of the string, was up, and mg was down. So the force that actually caused work on this object to happen was gravity. Gravity did positive work on this box. I did negative work because I pulled upward, but the box went downward. So that's a concept as well. So let's talk about how we're going to measure the effects of work, because there are a lot of different ways that you can do work. So let's start again with the box on a flat surface. Let's suppose this surface has no friction. It's like a puck on an ice field. And we're going to give that box a push to the side. And the box will travel all the way from here to here over a frictionless surface. That's important here. And so if we look at the free body diagram for this box, during the push we have a normal up, we have an mg down, and we have my force to the right, and since there's no friction we won't have anything else. The displacement, the delta x, is horizontal. So neither the mg nor the normal could do any work in this situation. No work is done by gravity, no work is done by the normal force, because the box does not move vertically. So there's zero work done in the vertical direction. There is going to be work done by me in the horizontal direction, because my force is the same direction as the displacement. And I can calculate that, again, with the equation we just got, which is work equal F delta x. Well, I can apply this, I can also describe the motion of this box. If I apply a constant force to something that has mass, let's give it a mass m. If I apply a constant force to it, assuming this is not instantaneous, so there will be some time interval, this thing will accelerate. So my constant force in this case has caused velocity to happen. So let's see how much velocity I will get out of this. Well, if I'm looking at the object, some givens, I know it's going to start at a v naught and end at a v final. And if, let's assume it started at rest, we could say v naught was 0. And so I've got a distance involved, that's important. So I've had a v final, a v naught, and a delta x, and I was looking for an acceleration, I have an equation for that. That would look like this. That would be a v final squared is equal to a v naught squared plus 2a delta x. And the only thing I'm missing there is this a. Well, a, I know, the reason that it was accelerating in the first place is because I applied a force. I applied a sigma f, which caused a mass to accelerate. And really my sigma f in this case was just my force, because the normal and the mg cancel each other out. So I should have an f divided by an m. That's the acceleration. So let's plug that in. So my v squared equal v naught squared plus 2 force divided by mass times delta x. Look how the work part shows up in there. That's important. So let's isolate work here. My v naught was 0. And so I'm going to go ahead, go down here, and multiply by m and divide by 2, and I will get that 1/2 mv squared is equal to the force times the delta x, or the work that I did. So in this particular case, if I set up a situation, let me scroll again. If I set up I hate when it does that. If I set up a situation where I'm pushing this object sideways with no friction force resisting, and where gravity is not assisting or anything like that, if I do this perpendicular to gravity, then all the work I do turns into velocity. All that w equals f delta x. Oh, let's do it again. Here. So work can be used to create velocity at this ratio, at the 1/2 mv squared ratio. Okay? And that's kind of like I've stored my work. I did all this pushing. I pushed over a certain distance, and the box got up to some speed. And of course, according to Newton's laws, an object in motion will tend to stay in motion. So I've essentially stored all of that push that I did as speed. It's a way to store a force over a distance. It's a way to store work, if you could picture that. All right, assuming you're in a place where there's no friction to take away your work, right? Because if there was friction, there would be a constant force pushing back, and then all of your hard work is undone. So that's if I push perpendicular to gravity. What happens if I push with gravity? Well, if I push with gravity, so this is the case where I lift the box straight up or lower it down. Let's go this way. Let's say I do work against gravity. So I'm going to have a force straight up, and later the box will be up here, and it will travel like this. And the free body diagram here would be this, my force, and mg down. And that would get the box up to where it has to go. So my force essentially has to equal mg to get it there. This is assuming I'm not creating any speed in this case. Well, let's think about this. The work I do would be equal to the force I apply times the distance the object travels. For a lot of physicists, when we're doing a vertical problem like this, because this kind of energy versus gravity is always vertical, we'll say this is a height. We like to say delta x is actually an h. So the work that I do would be equal to the force, which in this case is the force I apply has to be equal to mg, so mass times gravity, times the delta x in the vertical direction, or times the height. So that would get the object up to here. Now, what happens if I let go of that object from this new height? Well, the object will then experience a force, a constant force straight down. And the box will go all the way back to where it started. And that force will just be mg. So if I let it go from that height, the work done now is just done by gravity, and that force is mg and then of course the distance of travel, which again is going to be h. So the work I do to lift it up a certain amount is going to be equal to the work gravity would do if it fell from that same exact height. So essentially I can store work as height. Earlier I was able to store work as speed, right? If I do a certain amount of work, here it was, I get a certain amount of speed. Here, if I do a certain amount of work, I get a certain amount of height. And that can be taken back later. I can get all that work back if I just let gravity free to do its own thing. So I keep using this word work, and I'm going to do one more type here, and then we're going to get into the concept of energy. Also, this is still measured in joules. So let's say there's one more type we can do, and that would be like a spring. There are actually more types of work you can do, but we're going to focus on these three. Let's say I have a spring, it's not compressed or stretched or anything, and I take my box and I set it right up against the edge, and then I start pushing. I apply a constant force, and the box will compress the spring. And let's also assume there's no friction. So here we go. And after a while the spring is all coiled up, and here's the box after I applied my force like this, and I've compressed that spring a certain distance. If I let that spring go, then I will expect that it will push right back to where it started. Basically using the same force that I used to get it there. Now the difference with the spring, of course, is that the farther I compress it, the harder I have to push. So this is a variable force, which we will get into in a little bit. But the concept is still the same idea. If I do a certain amount of work to compress the spring, the work up here was equal to my force times the distance I moved the block, then the work that the spring does to get it back to where it started will basically be the same thing, an F times the distance. Now, we have to then qualify that F, because that is a changing F as opposed to a constant F. So how do we deal with that? Well, let's look at how force changes with distance for a spring. Well, we have the Hooke's law equation that F equals K delta X for a spring. And this K value is like the stiffness of the spring. So depending on how stiff your spring is, the farther you compress it, the more force it takes. But this is a linear relationship. This is not like an x squared relationship or something. So if you were to graph this, force versus distance for a spring, you would get a straight line. And the slope of that straight line would be the K value, the spring constant, the stiffness of the spring. Well, that means that at zero stretch, which is where the box started, there would be zero force, and at some stretch x, you would have some force F, and it varies linearly. What's the average of that? Well, the average of that is essentially halfway. It's the halfway point. So if you were to take a linear spring that obeys this Hooke's law relationship, and there are some springs that don't, but we won't deal with them in this class. So if you took a linear spring and compressed it at distance delta x, the average force that you used over the entire interval would be half of the force at the maximum. Half of this force, just by symmetry. So let's put that into the work equation. So we have work equal to F delta x. But we also have that for this spring, the average force, we have F equal kx, and we have the average force is going to be about half of that. So if we want to get the average, we can replace that F up here as half kx. half k delta x. And then we add that other delta x. So this is really half k delta x squared. So here's what I'm doing. I'm saying that half of the maximum force is this. So I can change this average force to half of F max. And then I replace that F with k delta x. All right, so if I'm going to store work in a spring, it is done at this rate. The amount of work I can store is equal to half of the value of the constant of the spring times the displacement from the spring's equilibrium, or the change in distance that I apply. There you go. Those are the three types of mechanical work that we can do. And there are other types of work. For instance, friction is a type of work out there as well. When friction does work, it just tends to heat things up. It doesn't tend to create movement. Most of these, all of the works we've seen created movement. We had a delta x for the spring. I'll write the others down here. For the height, if we did work vertically, we had an m, g, h. H is a distance that something moves. And then when we did work sideways with no friction, we created speed, 1/2 m v squared. And velocity is a distance over time, so we're creating movement there as well. So these types of work involve movement, whereas you can also do work to create thermal movement. You could create heat with work, which is not a type of, we'll not consider that a type of mechanical energy. So I just used the word energy, so let's talk about what I mean by energy. Energy is this concept that no matter whether I'm doing work to create height or whether I'm doing work to create velocity, I'm using that work, that it's all measured in joules, okay? Everything here is some amount of joules of work that it took to create the distance or the height or the stretch of the spring or the velocity. And those can all be compared to each other. So joules are kind of like money in the physics world. In the physics world, let's say you want to get something moving at 20 meters per second. That's this type of work. It's going to cost you a certain amount of joules to get that amount of work. Let's say you want not to create speed in an object. You don't want to push on it for a distance and make it go fast. You want to push on it for distance and lift it up. That's a useful type of work. Well, that's going to cost you a certain amount of joules. Let's say you want to stretch a spring out or compress a spring down, right? You're not gaining height, you're not gaining speed, you're just making something stretchy stretch. Well, that's a different kind of work. But it'll still cost you a certain amount of joules. And you can do these interchangeably. So there are things like, I could push on an object to get it moving, or I could release it from the top of a ramp and let it slide down the ramp. It will lose some height. Gravity will do work on it as it goes down the ramp. How much work? A certain amount of joules. How many joules? Well, we can use that amount of joules to figure out how fast it should be going at the bottom. So the idea of work allows us to compare a lot of different areas of physics that maybe we normally wouldn't think were that easy to compare, right? We have height here, we have speed here. Those seem like they're different units, right? One's in meters and one's in meters per second. That's apples and oranges. Well, not if everything's in joules. Joules is just a concept that allows us to go back and forth between various disparate areas of physics. And that's the concept of energy. It's very arcane. It's very abstract. Energy is this idea, and it all comes back to work. It all comes back to this, that we were pushing on something for a certain distance. But energy is this concept that if I watch like a car going down the street at a certain speed, I can say, oh, that car has energy. What I'm really saying is, oh, that car got pushed a certain distance. But there are a lot of ways to express energy. I don't know how that car got going so fast. Maybe it rolled down an incline. And a certain height is associated with this particular speed, right? If it started at that height, that would have given it enough energy, enough joules to get up to speed v. Maybe it didn't start at a certain height. Maybe it started, instead, scrunched up against a spring on a wall. And I just let that spring go and it pushed the car. And that delta x, right, that distance here, the spring was scrunched up, gave it enough joules to get up to speed v. Well, that's a way to get energy. So energy is going to be this, it's not a thing. You can't put it in a box. You can't take a picture of it. That's not what energy is. Energy is simply a concept, just like money is a concept. I have $100. Well, maybe there are some pieces of paper that I can use to represent that. What does that really represent, that money? It represents that I did some useful work for someone and they paid me for it, which means I can trade it for something else. Energy is a bartering concept. Well, that allows you to compare different parts of physics. And it works for everything. It works for chemistry, it works for biology. In biology, for instance, and in chemistry, I guess this is a cross concept, you have molecules in your body, right? Here's a molecule you might have in your body, an acetic acid molecule. And you learned in chemistry that all of those pieces are held together by chemical bonds, right? Well, that's a force. That's a force between them, holding them together. If these bonds break apart, it takes a certain amount of work. If they come back together, it takes a certain amount of work. It takes a force over a distance to push those things apart or pull them together. And sometimes the amount of force it takes over a distance to push them together is less than the amount of force you get back when they fall apart. And that force can be used to go somewhere else and do something differently, right? So every time in your body, another one is fat molecules. We could draw a fat molecule. If you remember your organic chemistry, fat molecule is a big long chain with an OH at the end, and there's 3 of them. And those are all carbon bonds. So every time you go in and break a carbon bond, that's going to produce some force over a distance on something else somewhere else. And if you do that enough times, you can create movement. Well, instead of calling it a force over distance, we just say that that molecule has a certain amount of joules of energy stored up in its bonds. And if you had an enzyme that could break all of those bonds apart, you would have access to all that energy to turn into something else. Like you could move your arm. You could make your arm go up. That would be vertical energy or height. You could make your legs push you forward, which would turn into speed energy. See how that works? So anytime somebody is talking about energy, it's some force over some distance. And if you can even apply this to thermal energy. If you remember back in chemistry, if you had gas particles bouncing around in a balloon, right? Here's your balloon. It has all the gas particles in it. They all have some speed. Temperature was based on kinetic energy, they used to say. Well, kinetic energy was just movement. How fast are the gas particles moving? So 1/2 mv squared represents the average movement of those molecules. Well, how do you make them go faster? You could apply pressure to them. Pressure is based on force. Well, essentially, if you do some work on them, if you do a force over a distance, you could make that particle go faster. You could give it more kinetic energy. And if all the particles had a higher average kinetic energy, we would perceive that as a higher temperature. And one of the things that's misunderstood about energy is students tend to think, well, chemical energy and physics energy and biology energy, those are all different things. You know, that's not the same energy. It is the same energy. It all comes from this concept that you either did work on an object, you did a force over a distance to get something to happen. So let's call those things now that we have a better understanding of where it all comes from, let's just label those in terms of work. We will say that the work that causes speed, 1/2 mv squared, that causes motion is kinetic energy. And something with velocity has a certain amount of kinetic energy, has a certain amount of joules of kinetic energy. All that means is that if it has 10 joules of kinetic energy, 10 joules of speed, right? That means that somewhere along the line, something did a force over a distance, and it did 10 joules of work to get it up to that speed. If we have height, something is this high off of the ground, h off of the ground, we say it has gravitational potential energy. We call it a potential energy because it's not actually moving. If you lift something off of the ground, it doesn't actually have speed yet, and speed is an easy energy to see. Something moving twice as fast as something else, that's obviously got more energy to your eye. But if you let go of that object from that height, it will turn into speed. The gravity will do work on the way back down. So it's gravitational potential because we had to do the lift to get it up there. And then we let it go, and it falls back down. Then gravity exerts or does work on the object. So it's about to get gravitational energy. So gravitational potential energy is based on mgh, is based on how high we lift something. And if we stretch a spring or anything else that's elastic, it could be a rubber band, it could be anything, and we store it as half kx squared because we squeezed or stretched a stretchy object, then that work is being stored in the stretchiness of the object itself, in the distance that it's been stretched. We will call that elastic potential energy. Because just like the gravity, as we release that stored work, that elastic will snap back and push on the object and do work on it. So that's elastic potential energy. And if you want to get into some of the other types of energy, if you store it as motion in a gas, right, as temperature, that's thermal energy. If you were to store it in chemical bonds, like the natural gas that you have coming out of your stove, is all chemical bonds, and when you break those chemical bonds, you can turn that energy into other things. Okay, that would be chemical energy. But it's all based on F delta X. And I want everyone to have a solid foundation that energy is just a concept. It's just an accounting tool. What it really represents, anytime somebody is saying the word energy, what they really mean is that I did some force over some distance to create some condition. I either used that force over a distance to create speed, or I used it to create height in a gravitational field, separation in a gravitational field, you could say, or I used it to create a stretch of a stretchy material, or I used it to heat something up, or I used it to push some chemical bonds together. Or later we will learn we can use it to make separation of charged particles in an electric field. And there's magnets that can have energy associated with them as well. But any time someone says energy, you go back to the idea that means someone did work. Someone did work to store that energy in some type of situation. Okay? And we will spend a lot of time on this because being joules, they can go in any concept. They can go in kinematics, they can go in forces, they can go in electricity, waves. Everything has energy associated with it.